is, Boiler Controls, from the simple to the sublime. From the simple to the sublime. And we're going to talk about everything from your simple high-limit aquastat and triple acting aquastat on a standard cast iron boiler, all the way up to outdoor reset for modulating condensing boilers. Now, one of the cool things about modulating condensing boilers is that the technology on those is changing so rapidly, and they're trying to jam so much information into a small touchscreen panel that there's an awful lot of stuff that there's an awful lot of things that they can do, but you have to understand the nomenclature. For basic programming, they're all pretty much the same. They ask for similar information, but there's so many different features and benefits to the different manufacturers' products that it's impossible to cover here. So we're just going to cover some of the generalities, and we're going to discuss ways to help you make either a cast iron boiler more efficient or a modulating condensing boiler as efficient as it can possibly be. So let's start with a discussion, if we may, on your customer's #1 concerns. I mean, really think about it. When your customer calls you, what's the one thing they want more than anything in the world? When they're looking at their heating system, the one thing they want more than anything in the world, yes, they do want comfort, but nowadays with fuel oil, the cost of what it is, with natural gas being what it is, and all of the talk about the super efficient products out there, your customer's biggest concern or biggest desire out there is energy efficiency. I want an energy efficient system. Now, that's a loaded question, because they can certainly reduce their fuel bills simply by living like these people in the cartoon. Turn the thermostat down to 40 degrees, start a fire in the living room, you're going to cut your fuel bills by quite a bit. So it's not just lower fuel bills they're looking for. They're looking for lower fuel bills with also a heavy dose of comfort and convenience, okay? Because they have the lower fuel bills deal already. Just turn that thermostat down to 50 degrees or 40 degrees and suck it up, right? That's kind of where we're at. Just suck it up. That will cut your fuel bills considerably. Otherwise, that's not going to cut it. So they really want energy efficiency while at the same time enhancing their comfort and peace of mind by having a reliable system. You guys are on, Mr. Baker's on the title page. I'm not sure if everybody else is or not. I know on my second screen here I'm kind of moving along. So hopefully hopefully everyone is keeping up. If you see, let me know if you see a picture of an old boiler, a very old silver boiler on the screen right now. Basically what you're looking at here is a question that most customers face. Do you want to modernize, meaning rip out what you have and start over again, or do you want to improve the system? Do you want to improve your system? It depends, really it depends. If there's an 8 or 9-year-old cast iron boiler, well, that thing's really maybe still a baby, all right? It's not something that you want to rip out and throw away in the name of getting a few more points of energy efficiency. Maybe there are things we can do to that boiler to make it as efficient as possible. Now, if it's a 35 or 40-year-old boiler that has been in constant need of repair pretty much every winter, and we're concerned that it's going to ultimately die in the middle of winter at the most inconvenient time, well, now there's an opportunity to modernize. And then the question becomes, do you modernize with a standard efficiency boiler controlled as efficiently as possible, or do you start up with a high efficiency boiler? Those are the questions that you have to help your customer answer and help your customer make a good decision. Okay? When it comes to cast iron boilers in particular, but also modulating condensing boilers, controls do make the difference. Controls do make the difference. We do have the ability to make a cast iron boiler as efficient as it can possibly be by controlling it and pumping it intelligently. The Taco Fuel Miser, the SR501OR that you see right here, is an outdoor reset go-between relay for a cast iron boiler. It could also be used in a modulating condensing boiler if necessary, but used for a cast iron boiler to enhance its overall efficiency. It's kind of a nifty add-on. We're going to talk to you a little bit about that. There are other things you can do as well. Adding a variable speed delta T circulator can help enhance the overall efficiency of the system. There are things that we can do to make that cast iron boiler as efficient as it can possibly be. Okay. Let's start with some basics here before we jump into that. Understand the basic controls that we have with with a cast iron boiler. We're talking about on-off single stage, pretty straightforward controls, whether a high limit aquastat for most cast iron boilers, or if it's a cast iron boiler that needs to maintain temperature for whatever reason, whether it's a really, really large boiler in a light commercial application and you don't want it to turn cold, or whether it's a cast iron boiler with a tankless coil built into it to make domestic hot water. You would have a boiler with a triple acting aquastat. So we're going to talk about both of those, a high limit aquastat and a triple acting aquastat. They're kind of the same thing, only different. Before we jump into aquastats, there's just a concept I want to get on the table. Most of you understand it and are cool with this, but I just want to get it on the table so we're all starting together at the same spot, and that's understanding the concept of a differential. All boiler controls work off of a differential. And by differential, what we mean is, when does it turn on, when does it turn off? Let's say we set a boiler high limit to 180 degrees. Off the top of your head, you say, okay, that means when the boiler hits 180 degrees, it shuts off. When the boiler goes below 180 degrees, it turns on. Well, yes and no. If the boiler works strictly in that manner, it would short cycle like crazy. It would short cycle like crazy, particularly when you have low load conditions. Okay, it would short cycle like crazy. When you build a differential into your control, really what you're doing is you're giving it a range. Okay, you're saying if I have let's say my high limit. In this picture, we're showing the high limit, the set point for the boiler set at 165 degrees. Or I'm sorry, take that back. 160 degrees. The high limit is set at 160 degrees, as it's shown here. We have a control with a differential of 10 degrees. And basically, that's a plus or minus 5 degree differential for a total of 10 degrees. Essentially, what happens is when the boiler fires, it keeps burning, 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 burning until the internal temperature of the boiler goes beyond the 160 set point in this example. And it keeps burning until it reaches a temperature 5 degrees above that set point, in this case 165. At that 165 degree temperature, the boiler shuts off. And as you can see, the boiler temperature, it crests just a little and then it starts to drop. And the temperature drops, drops, drops below the set point of 160. Doesn't turn on then. It instead kicks on when the boiler temperature reaches 155 degrees. Okay? And then the whole cycle starts again. The point of a differential is that we try to prevent / eliminate short cycling. The trick is to get a wide enough differential to reduce the likelihood of short cycling, but a narrow enough differential so the boiler has enough energy inside of it to quickly satisfy your heat loads, and so you have consistent temperature control in the living spaces. So there's kind of a balancing act right there, kind of a balancing act. So we're going to discuss applications of differentials as we go on. Let's take a look at a high limit aquastat here. This is your standard high limit aquastat that's on most normal cast iron boilers. The newer boilers, going back to last August or last September, have to have some sort of control that changes water temperature in accordance with the heating load. We'll talk about where you can find more information on that. But this is your basic standard high limit aquastat. Let's go through the anatomy. Up in the upper left-hand corner, you have your power in, your line voltage. That'd be L1, L2. Then you have your TT terminals, where the thermostat, if it's a single zone, is connected, or if you have a multiple zone system and you have a zone valve control box or a multi-pump relay, the end switch terminals, the output from that multi-zone control box would be wired into TT. Those terminals close whenever any of those zones call for heat. That will in turn tell the boiler that there is in fact a call for heat. So there's your TT terminals. Your adjustable high limit dial is over there on the left-hand side. You can barely see the little knobby. It's just a stamped piece of metal with numbers on it. You adjust it to the high limit that you're looking for. Okay. We have an onboard line voltage to low voltage transformer to help the two sides communicate, the line voltage and the low voltage. Your relay contacts, those are pulled in when the relay coil is energized with low voltage to help turn on both the burner and the circulator. There's your circulator contacts down below, C1 and C2, and then you have your burner contacts, front oil burner or gas igniter on the B1 and B2 terminals. Pretty simple, pretty straightforward. We're going to go through a ladder diagram next on the sequence of operation for the high limit aquostat, just again so we all know where we're starting from. If you take a look at this ladder diagram, up at the top you see L1, L2. That's your power in, as we discussed earlier. Down at the bottom you see TT. That's your thermostat connection. Okay, that's right down over here. Connected to TT outside of the control is your room thermostat. We'll call that the thermostat or the end switch from your zone control panel. Connected to C1 and C2 we have the boiler circulator, or the system circulator in this case. And then connected to B1 and B2 in this example we have an oil burner. If we look inside, we see this little squiggly line down here in series with the thermostat or the end switch, the TT terminals, and your low voltage side on your transformer. The thick black lines are line voltage, the thin black lines are low voltage. On the low voltage side of the transformer we have a relay coil. Okay. When that's energized, it becomes an electromagnet and it operates this relay contact, right, you see up in the upper left-hand corner. When that relay coil closes on a call for, or when that relay coil is energized on a call for heat, it pulls close the relay contact and then the party starts. Okay, let's take a look. All right, as we see, the room thermostat has closed down here at the bottom. We now have completed the circuit between the power supply, which is the 24-volt transformer, the switch, which is the thermostat or the end switch, and the load, which is the relay coil. That relay coil is energized. Once the relay coil is energized and becomes an electromagnet, click, the relay contact up here on the line voltage side closes. So we've now closed two separate circuits, or we've closed two circuits. We've closed the circuit at C1, C2 for the circulator, so the circulator comes on. And we've also closed the circuit at B1, B2, and now the burner comes on. And while this is going on, we're circulating heat through the system. The burner's firing to keep that boiler up to a reasonable temperature. And let's say the circulator's circulating, but the boiler temperature is going up, 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 up. It passes the high limit set point of, let's say, 180 degrees. It charges past that, and then it hits the differential setting above that high limit. Again, let's say if it's a 10-degree differential, and 180 is our set point, it's going to keep charging past that until you hit 185. When the temperature in the boiler hits 185, then this little high limit switch, which is normally closed, and well, again, whether it's normally closed, normally open, that's open to interpretation, but when the system is below high limit, this switch is closed, allowing the burner to fire. When we hit 185, that switch opens. Now we still have a call for heat, so the circulator is still going to continue to circulate, but once the high limit pops, we've broken the circuit between power, the relay contact, and B1 and B2. At that point, the oil burner is going to shut off because we've reached our high limit. And it won't fire again. If the call for heat continues, the burner will not fire again until we get below 155. Or I'm sorry, 175 in this example. The boiler will stay off until we get till we reach 175 if the call for heat is continuous. Okay, cool, cool, cool. All righty. Only check Facebook once. Others are studious and do not know it all. Very good. Mr. Reese, just check Facebook real quick. Here's what the burner, the operation cross section looks like. Up on the top, you have your thermostat on. That's your call for heat segment. The circulator stays on at the same amount of time as that call for heat with the thermostat. But here we see the burner on, burner off, burner on, burner off, burner on, burner off. If we're working off of a 10-degree differential, you can just follow the lines below. Okay, the burner's on until, in this case, we hit 165, 5 degrees above the 160-degree set point in this example. Then follow the line, the burner's off, off, off until you hit 155. Then the burner kicks back on, back up to 165, and so on, and so on, and so on, and so on, until the call for heat's all over. Again, pretty simple and straightforward operation, if you will, of a standard high-limit aquostat on a cast-iron boiler. Keep this package in mind so you understand how this works. We can apply it later when we look at the fuel miser and its cousin, the PC700 outdoor reset control. Again, and there you see the set point, your high limit, and your low limit on the left-hand side and the right-hand side. Here's your triple acting aquastat. This is found on a lot of older boilers that have tankless coils for making domestic hot water. Also found on larger mass boilers, you know, light commercial or Mongo residential boilers where they just don't want them to go stone cold. They always want them to keep some heat in the boiler. They're called a hot boiler or a low limit boiler, rather than having a boiler be what you would call a cold start boiler. Very similar in layout, but it has a little bit of extra stuff in it. Behind that little tag up top, you have your TT terminals for your thermostat. There's your onboard transformer. The relay contacts are over there on the right-hand side. C1 and C2 down below the relay contacts. L1, L2, that's your power in, your line voltage in. Right next to that, by that yellow wire, in between, on either side of the yellow wire, you have B1 and B2. Those are your burner contacts. And so far, it's pretty much the same. The difference is going to be in the next three items. You have three dials. First, you have your adjustable high limit. It's a little bit more formal. It's a little red dial, and you can actually read the numbers there, ranging from 140 to 220. It's your adjustable high limit. You also have your adjustable low limit. What minimum temperature do you wish to maintain in that boiler? Let's say you want to bop between 200 degrees on the high limit and 140 degrees on the low limit. Okay, that's your high limit, low limit. Again, whatever it needs to be is whatever it needs to be. And then you have your adjustable differential. Now here you can dial up and change the differential from 10 to 15 to 20 degrees, depending upon what you need it to do. So it's an adjustable differential. Many high limit aquastats will have a built-in differential, and you can buy different models. They may have an 8-degree differential, 10-degree differential, or 15-degree differential. It just depends on what you buy. This one has an adjustable differential. Alrighty, let's take a look at the ladder diagram for the wiring and understand the concept or the sequence of operations. Again, up top you have L1, L2. Way up top, there's your power in. C1, C2 for your circulator. B1, B2 for your oil burner. All right, down below you have your TT terminals. Okay, the thin black wire is your low voltage side, thick black wire is line voltage. Room thermostat, there's your relay coil and your transformer. Now notice the relay coil. We have one relay coil, but if you look closely, we have two relay contacts. Two relay contacts, one in series with the circulator, the other one in series with the oil burner. Okay, there's two relay contacts. And if you'll notice as well, there's two internal limits. There's your low limit switch and your high limit switch. Your high limit switch is a single pole, single throw. It's either open or closed. You're either above the high limit or you're not. Okay? The low limit setting, as you see, is an either or switch. It's either connected to the circulator terminal or it's connected back to that burner leg, as you see there. That is a single pole double throw switch. So we're kind of in an either or scenario there. When might we use that? Well, let's take a look. Okay. And there's your high limit, your low limit settings right there. Let's get the thermostat involved here and get a call for heat. Okay, we have a call for heat, and when we have a call for heat, you see the relay coil is energized. When the relay coil is energized, on a call for heat, both of those relay contacts in the line voltage side will close. They'll go click, and both will close. What happens next? The circulator turns on, the burner fires. Okay, creates heat for our call for heat. So the circulator's circulating, the burner's burnerating, and everybody's happy. Okay, we go on in time, and then all of a sudden, we go below the low limit. We're taking so much heat out of the boiler that the temperature in the boiler goes below the low limit setting. Let's say it goes below 140 degrees. Now that single pole double throw switch on the C1 terminal would now do this. Okay, now it's opened it's cut power to that circulator terminal. So what happens to the circulator? Well, the circulator is going to come off or turn off. We're going to stop removing heat from the boiler, and we're back onto this circuit here, which is already closed. We're already below the low limit, obviously. We're just going to focus on making heat in the boiler. This prevents us from circulating cold water through the heating system, but it also prevents us from. It's basically what it is. It's a simple man's domestic hot water priority. This would happen during the heating season if we had a major call for domestic hot water, and during that call for domestic hot water, the boiler temperature dropped below the low limit. Well, now what we're doing is we're saying, you know, sit, stay heating system. We're not going to give you any heat. We're going to focus everything on making domestic hot water, and we're going to do that until the boiler temperature gets above the low limit, above the differential above the low limit, let's say. If it does that, then we go back like so, if that makes sense. And then the high limit setting works the same way. If the high, you know, if we go off on high limit, well, burner shuts down. Okay. Now the other thing to remember here is that single pole double throw switch is not necessary. It's not controlled by the thermostat. It's controlled by the temperature. So what's going to happen here in the summertime when there is no call for heat, this boiler is still going to maintain the minimum temperature it needs that you set the low limit for all summer long. And that's so you have instant standby domestic hot water. Is that the best way to run that type of an operation? Well, it's the simplest. I'll give you that. It's the least expensive way to get a boiler with to make domestic hot water. You don't see many new boilers with tankless coils installed in new construction installations. I think it's okay to put them in when you have, if you're swapping one out, you can replace an existing one. But new construction, you really can't do it, and it's not the most efficient way to make domestic hot water. And here is the burn pattern for this particular type of boiler. Again, no call for heat down here. All right, we were bouncing off the low limit setting plus the low limit differential. Okay, burner's firing. Here's the low limit differential, and then it cools back down. We're at low limit. Bang, comes back on, off, on, off, on, off, just to make domestic. So it's warm for domestic hot water. Now we have a call for heat right here. Bang. Now we go up to the high limit plus the differential, and we bop off of that. And then in this example right here, where we have this big drop, well, that's when we have a large call for domestic hot water, perhaps. Now the temperature's dropping down, 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 down. We get below the low limit setting. As you see right here, the circulator goes off. So we focus on making domestic hot water. So there you go. That's basically how the triple acting aquastat works. So alrighty, enhancements. How can we enhance one of these existing cast iron boilers? Well, there's a couple of add-on controls that can add the concept of outdoor reset to a cast iron boiler. The Takeo Fuel Miser is one. This is a go-between relay that has an outdoor reset control built in. Essentially what it does is it does not replace the high limit aquastat that's on the boiler. It simply sits between your zoning package and the high limit aquastat. So the zoning package has to go through the heat miser, or rather the fuel miser goes through the fuel miser before it gets to the boiler. The fuel miser says, all right, I understand you have a call for heat. Thank you very much. The boiler and I are going to figure this one out for you. You just go circulate whatever you got to do. The boiler and I are going to figure out what water temperature you need. And that's what the fuel miser will do. It's fairly straightforward. You see, if you take a look here, you have terminals right here for your sensors, your outdoor sensor as well as a boiler supply sensor. So it knows how cold it is outside. It knows what temperature the boiler is making. Your thermostat or your zoning output from your relay or from a thermostat goes right into here where it says T-stat. Next to it you have domestic hot water. If you have an indirect hot water tank, you would simply run your aquastat lines to the DHW terminals here, and that will override whatever outdoor reset you may have, which is a good thing. So it will make domestic hot water. And then the other terminals here, XX, those go to TT on your boiler control. The dial, I'm sorry, one more time, the dial, which is right here on the right next to the boiler terminals, and you see a larger picture of it here. This is how you set it, and it's pretty simple to set. All you do is set this dial to the outdoor temperature that you would like the boiler to supply 180-degree water at. So it's based on your heat load calculations and your outdoor design temperature. If the quote-unquote coldest day of the year, the temperature you design your heating systems for is 0, you simply move that dial to 0. So at 0 degrees, it'll make 180-degree water. If your outdoor design temperature is -10 and you want 180-degree water at -10, you set the dial to -10. Just a slight word of warning. we have a lot of guys will look at this and say, well, I want to be safe. I just want to be safe. I don't want the phone call in the middle of the night saying this control isn't giving me hot enough water. So instead of setting it 0, I'm going to set it at -10 because I want to have enough. And that sounds intuitive, but it's actually counterintuitive. You've just gone backwards. If I set that dial at 0, that's telling the control at 0 degrees outside, I want 180-degree water in the boiler. If I in hopes of getting extra, I set it to -10, I've done completely the opposite of what I want. Now I'm telling the boiler at -10 I want 180-degree water. At 0-degree water, I would actually have something less than 180 degrees, which is kind of the opposite of what I want. So if you want to be quote-unquote safe, if you're nervous, you don't like 0, but you want a little extra, turn it up to 10. Now you're saying, okay, at 10 degrees outside, I want 180-degree water. Just a way to, just so you understand and don't make the mistake in the wrong direction. Okay. So that's the hard part as far as setting up your system. There's some dip switches on here as well that have to do with what kind of a boiler you're setting it up with. Dip switch number 1 sets your minimum boiler temperature. If you're connecting it to a cast iron boiler, you want dip switch number 1 in the on position. That sets your lowest temperature at 140. So that boiler is going to bop between 140 or 190 or whatever, or 140 and 180 or 190, whatever you have it set at. That sets the low limit so we don't condense flue gases. If you're using it on a modulating condensing boiler or you want the temperature to go down lower, you just simply set it to off. Now 70 is the lowest temperature, or the boiler minimum. Dip switch number 2 is an adjustable differential. You can set it to either 10 degrees or 20. Now, under what circumstances would you pick one or the other? Well, that really depends. Generally speaking, if it's a lower mass, smaller boiler with not a lot of water content, you're probably looking at a 10-degree differential. You know, just so you have enough. It'll heat up quickly. You want to make sure you have enough when it's really cold. If it's an older boiler that's got a heck of a lot of water content and a heck of a lot of mass, the 20-degree differential actually isn't too bad. It's not a bad thing. You can make use of a lot of the residual heat in that boiler before asking it to fire. It's really not a bad way to go. So those are your options there, either 10 or 20. And then dip switch number 3 is the pump operation. You can, if you have a primary secondary piping arrangement and outdoor reset, and you want the boiler circulator or the primary circulator to fire every time there's a call for heat, you're definitely going to want to disconnect that boiler circulator from the boiler, or primary circulator from the boiler control, from the C1, C2 terminals, and wire it into the fuel miser. And then you want it to come on whenever there's a call for heat. So in the on position, that circulator will come on whenever there's a call for heat or domestic hot water. If you have an indirect that's run on primary, secondary. Or if the indirect has its own circulator and the primary pump only has to run for the heating demands, then you put this in the off position. That circulator would only come on during a call for heat. Is that right? Okay, and there is your fuel miser. Again, it's a nice simple way to go to add outdoor reset to an existing cast iron boiler. A step up from that's the PC700, which is a solid-state electronic, fully programmable outdoor reset control for a single boiler. It's a single-stage, one-boiler control. We have the 702, which will do 2 boilers. But this is an add-on control, and it does require an EXP relay or an EXP zone valve control, because you have this Molex connector here. That's how you integrate it into the system. It's the easiest thing in the world to wire. You just plug it in. Okay, so you have to have an EXP multi-pump relay or single pump relay or a zone valve control. Thing comes out of the box programmed for a cast iron boiler. All right, has a 10-degree outdoor temperature. Highest boiler temperature is 190, and then it has a low-high limit of 140. So the boiler minimum is 140. So it's set for this operating parameter right here that you see, so we won't condense flue gases. If you wanted to hook it up to a low temperature boiler, you could reprogram the control fairly easily. Okay. The neat thing about the PC700 is that it has a differential, but it's an automatic adjusting differential. It's not a fixed differential. It adjusts automatically, which is really cool. It's a really cool thing to have in an outdoor reset control. What is an automatic adjusting differential? Well, here's a fixed differential with outdoor reset. That the solid line represents the water temperature the boiler would create at different outdoor temperatures. So here we see at -20, that boiler's making 170 degrees. At 10, outside, that boiler's making what looks to be 135 degrees. Okay. The differential, if you have a fixed differential control, the differential is the same no matter where you are. It's 5, in this example, it's 5 above and 5 below. It stays the same, which is fine when it's really cold, but when it gets warmer out, that fixed differential, because you're not yanking as much heat out of the boiler and because that boiler has a fixed firing rate, all right, the input is fixed, you're going to possibly encourage greater short cycling. Okay, you're going to encourage greater short cycling under lower load conditions. An automatically adjusting differential understands that. And as the outdoor temperature gets warmer, the differential gets bigger. So we reduce the effects of short cycling when it's milder out, okay, which is a really helpful thing. It's a really helpful thing. Again, the PC700 is a step above the fuel miser. It's not quite as simple and as easy to install. You have a little bit more to go through, but it does a couple of things that the fuel miser does not do. Okay, very good. The question is, how much can outdoor reset save? Well, the outdoor reset. This was a study. This chart comes from a study conducted by the American Center for Energy and Environment, located in St. Paul, Minnesota. They did a study on different things that you can do to boilers to enhance their efficiency. And they studied these things and said, how much could it save? So a high-efficiency boiler tune-up, it says here, if you do a combustion analysis and tune that thing up, they say the annual estimated savings is 4 to 5%, which is a good thing. Now take a look at the column for reset control. The first row there is for cast iron boiler water temperature reset directly. Estimated cost, put an asterisk by that because I don't know where they came up with some of that stuff. But the estimated savings, 10 to 15%. Adding outdoor reset to a cast iron boiler, not going below 140 degrees to keep it from condensing, you can cut fuel consumption 10 to 15%, which isn't anything to sneeze at. If you got a $2,000 a year oil bill, 15% is $300. All right, that's attention-getting money right there. So, and those are things to consider. And if you look up the American Center for Energy and Environment online, you can actually download a copy of their report. It's an independent report. You can show it to your customers. Okay. Now, last September, in the U.S., there were new boiler codes for minimum efficiency levels and for minimum controls on boilers. If you want to learn more about that, I suggest going into TACO's The Neighborhood and reviewing the August 2012 webinar called New Boiler Codes, presented by Bruce Marshall and myself. Bruce Marshall is our trainer from Emerson Swan, manufacturer's representative for TACO in New England, and he is the smartest man I know. If he doesn't know it, it doesn't exist. And Bruce walks you through the new boiler codes and some of the new controls that are being equipped on existing boilers to help you reach those efficiency levels and how they work. So that is something for you to take a gander at. Modulating boilers have their own controls, so we're just going to understand them a little bit more perhaps. Modulating boilers have variable firing rates. The goal here is to match the output to the load. The load changes all the time. The load changes with the weather. Why not make the output of the boiler match that? That's the whole concept behind outdoor reset to begin with. And modulating condensing boilers are uniquely equipped for that. In fact, the lower the temperature of the boiler, the more efficient it is. It likes that. What we have with modulating condensing boilers is something called pneumatic modulation. Really what we're doing is we're changing the fan speed for the intake air to adjust the gas and air mixture to change its firing output. So if it gets colder out and we can't keep up, well, the fan speed's going to increase. The burner itself is going to modulate to keep up, and we're going to have more. The boiler's going to make more heat, and the opposite will happen if it gets warmer out or we get closer to where we need to be in terms of temperature. Again, they all basically work on outdoor reset. They calculate a temperature based on your programming, and if the boiler can't maintain that outdoor reset, the fan kicks up, the modulating burner kicks up. You start making more heat to get up to that point. If it's getting warmer out, the fan says, hey, we're good. We don't need to work so hard. It slows down. The boiler only makes 110-degree water if necessary. It'll just bop back and forth again based on its programming and its internal logic. Boilers will work on something called turn-down ratios and other love songs, to give Derek and the Dominoes their 2 cents worth. Turn-down ratios are employed to help that boiler figure out what size it needs to be. It is all about the BTUs here. Make sure you write this one down, gang. This is an important thing to remember when you're sizing the boiler, an important thing when you're discussing outdoor reset with a customer. Approximately 2% of the heating season is spent at or near your outdoor design conditions. No matter where you're at, it's roughly 2%. Now, it may get really cold where you are, but when you pick that outdoor design temperature, whether it's the ASHRAE temperature or the quote-unquote local custom, you're pretty certain that over the last 50, 60 years or so, somebody's kept track of this, and they've found that roughly 2% of the heating season, no matter where you're at, is at or near those outdoor design temperature conditions. Do you blow past it every once in a while? Oh, heck yes. Absolutely. Are there winters where you don't get anywhere near it? Well, yeah. Last year, the winter that never was, except up in Alaska. You have those situations. But more or less, 2% of the heating season is at or near design conditions. The other side of the coin is that 50% of the heating season, a full half of the time, over the course of a heating season, you are at 1/3 of the total load or less. 1/3 of the total load or less. That's kind of remarkable. We're sizing boilers and heating systems for something that hardly ever happens. And if we're a chronic oversizer, we're sizing a heating system for something that never happens. Okay? So not only is 98% of the heating season, not only is that boiler too big, most of the heating season, it's stupid too big. I mean, it's just way outsized for what is necessary. So the whole idea of modulating, condensing, outdoor reset, and turn-down ratios come into play. A turn-down ratio is simply, here's the highest burning capacity, BTU capacity of the boiler. It'll modulate down to this is the lowest it'll do. What's the ratio between the highest and the lowest? Okay? A 5-to-1 turn-down ratio means the minimum firing rate that a boiler can have is 20% of its maximum firing rate. If it's a 10-to-1 turn-down ratio, the minimum firing rate is 10% of its maximum firing rate. 4-to-1, it's 25%. It just depends on what kind of a boiler you're using and what kind of technology they have built in. It's kind of like having multiple boilers in one box, which is kind of cool. It's a way to get that boiler to more easily adapt to real-world changing weather conditions. When it comes to programming these controls, there's so many different brands, so many different controls. They all kind of get to the same place, but some have different ways of doing it. So they're kind of the same thing, only different. There's different nomenclature, different terminology, different programming methods, but most of them try to get you to kind of sort of the same place. They want to know coldest outdoor temperature, what's the temperature you want when it's the coldest outside? What's the warmest outdoor temperature you want the boiler to do something at, and what's the lowest temperature you want the boiler to fire to? And then it figures it out from there. That's the basis of all of these controls. So the programming from that level is similar, but one company's control programming process is completely different from somebody else because they're just different products. Okay, so they all have different, similar programming requirements, but vastly different features and benefits at the boiler itself. So you've got to understand what it is that you're using. A lot of guys tend to plan on using, I use this boiler or that boiler. Those are my two. That way I don't have to learn all of them, which is fine until you got to go service one of them. So what do? You know, that's your call on how you want to handle that. Well, let's do an example. A couple of examples. This is the NTI Trinity boiler programming nomenclature. What they want with the NTI Trinity is to set your high. They call it HI. That's the high. That's the boiler set point, and they give you these ranges. And then you pick an RES or reset. And what that does is it just sets the lower limit, the lower end of your temperature. Then you also tell it what the design temperature is, and it figures it out from there for you. So you just set these ranges, and you work on it like that. The triangle tube, you actually can select the system type. All right, say you're doing a fin tube baseboard system. You select fin tube baseboard, and it gives you the maximum set point and your minimum set point. Takes it from there, right? Which is pretty cool. That's kind of neat. You also tell it what your coldest outdoor temperature is, etc., and it'll figure it out from there. So the programming is fairly straightforward in that respect. This one is the HTP Elite. You program in for your basic parameters, your minimum outdoor temperature, maximum supply temperature, maximum outdoor temperature, and then your minimum supply temperature. That's functions 8, 9, 10, and 11 are your key functions. All the other functions are important too, but these are the ones that get the reset control to work. Okay? And then you can really, at this point, figure out your central heating curve. You can do this yourself by putting everything out there. So your minimum outdoor temperature, in this case, let's say we're using 0. There's your minimum outdoor temperature, and there's your maximum supply temperature, F9. And let's say we're setting it up for 160. Okay, so there's your minimum outdoor temperature is 0. Your maximum supply temperature is 160. Next, you set the maximum outdoor temperature, which in this case we'll use 70 degrees, and then your minimum supply temperature, the lowest temperature you want the boiler to fire, in this case we use 104. Right, just we program in these numbers. Once those numbers are programmed in, the control itself fills in the blanks, and basically it'll operate on that line. All right, so when it's 70 degrees outside, that boiler will make 104 degrees, unless of course there's a call for domestic hot water, which will override everything. When it looks to be about, this looks to be about 35 degrees right here. At 35 degrees, it looks like the boiler is going to make about 125 degree water. At 9 degrees outside, it looks like the boiler is going to make about 155 degree water, and so on. Now, this is the highest temperature. This 160 is the highest it's ever going to go. So when it's 41 below, it's still making, 160 degree water. Pretty straightforward. There's not, again, they're all a little different. They're all a little bit different. Now, with modulating condensing boilers, we have to understand short cycling is still an issue. Short cycling is an issue with cast iron boilers. Short cycling is an issue with modulating condensing boilers for a real simple reason. Anybody out there know why? If you want to type that in, go right ahead. If you think you know why, type it on in. Why do we have short cycling issues with modulating condensing boilers? And also give me some props. It took me a while online to find a picture of a guy riding a short cycle. Okay. Yeah, low mass. Albert picked it right off the bat. Right? Low mass. These things have very, very small water contents. All right. Very low water contents. Standard wall-hung boiler might have a quart, half a gallon, maybe a gallon worth of water in it. It's going to, no matter what your firing rate is, your air to gas mix, no matter what it is, it's going to heat up pretty darn quick. Okay. And even with a turn down ratio, you may find that boiler still is oversized for the application. Let's say we have a 100,000 BTU boiler. If it has a 5-to-1 turn down ratio, its lowest firing rate is 20,000 BTUs. Okay, it's still burning fuel at a rate of 20,000 BTUs. If you have a system with lots of small zones, or even a few small zones, called microzones, that thing's still going to short cycle like nuts. It's going to short cycle like crazy. And if that is a problem, if you have a short cycling problem, well, this looks like a job for the buffer tank. The buffer tank is simply a tank. It's nothing fancy. In this case, it's a super insulated tank. There's not a heat exchanger or a coil or anything in there. It's just a tank to hold more water. All you're doing here is you're adding mass to the modulating condensing boiler. You're adding water content to a boiler. Now, the irony here is for decades, they increased efficiency by making boilers smaller and smaller and smaller and smaller and smaller, and that increases the number that you can assign to it, but now they short cycle, and they're not as efficient as they could be. And another danger in short cycling high efficiency boilers is that you tend to wear out very expensive moving parts. Has anybody out there in webinar land replaced a blower motor, a fan motor, or an ignition module in a high efficiency modulating condensing boiler that's maybe 4 or 5 years old? Most people have, because it's short cycling. It's not that the thing's a piece of junk. It's that we wore it out. We short cycled it. Okay, there's a lot of time bombs out there. Think of these as time bombs. And The buffer tank is the bomb squad. It's out there to defuse these time bombs. Okay, we prevent short cycling even under partial load conditions simply because we've added mass to the setup. And it's simple as pipe to and from the boiler. The boiler's pipe to and from the buffer tank. Over here, here's your return back to the boiler. Down at the bottom you have the supply. And then you have your heating system supply and return as well. All right. Now the question always comes up is, well, a buffer tank's really wicked cool. How do I size it? Well, pretty simple. Here's your piping schematic. And really, if you're having trouble wrapping your arms around a buffer tank, just think of a hydraulic separator or a low-loss header. All a buffer tank is a big low-loss header. It's a low-loss header with some water content. Okay, that's all it is. It does, operationally, it's going to wind up doing the same thing. It's going to isolate the delivery side of the system from the boiler side of the system. So when each one's flowing, they don't interfere with one another. But that's really that's how it works. The benefit of it over a hydraulic separator is it simply adds a considerable amount of water content to help your burn cycles lengthen so we don't short cycle. But the question again is, how do we size a buffer tank? Well, here's some formulas for you guys to write down. All right, here's a formula for you to write down. You start by finding the minimum boiler firing rate. What is the minimum boiler firing rate? All right, what's the turn down ratio? What does that mean for a minimum boiler firing rate? Okay, minimum boiler firing rate minus the smallest zone load, the BTU load of the smallest zone, is your BTU surplus. Ciao, Anthony. Good to see you, man. Happy Easter to you too as well. Minimum boiler firing rate minus the BTU load of the smallest zone gives you your BTU surplus. That's the BTU surplus. Okay. Next, multiply that BTU surplus by the desired minimum run time, usually 10 minutes. Anytime the burner fires, we want it to fire for at least 10 minutes. BTU surplus times your desired minimum run time, usually 10 minutes. That is your cycle factor. That is your cycle factor. Next, to find the tank capacity, you'll divide the cycle factor by the delivery side delta T times 500. The delivery side water temperature drop. What did you design the delivery side for? If it's radiators or baseboard, maybe it's 20 degrees. If it's residential radiant floor heating, maybe it's 10 degrees. 500 is used if we have 100% water. So cycle factor divided by the delivery side delta T times 500 will equal your tank capacity in gallons. And that'll give you an idea of what size tank you need. Let's do an example so you can see how this is actually applied. Let's say I have a 100,000 BTU ModCon boiler with a 4-to-1 turn-down ratio. At a 4-to-1 turn-down ratio, the minimum boiler firing rate would be 25,000 BTUs. Pretty simple, right? 25,000 BTUs is the minimal boiler firing rate. The BTU load of our smallest zone under design conditions is 8,000 BTUs. 8,000 BTUs. To find my BTU surplus, I simply subtract 8,000 from 25,000. So the minimum boiler firing rate of 25,000 minus the BTU load of the smallest zone, 8,000, that gives me a BTU surplus of 17,000. There's my BTU surplus. Next, I'm going to multiply my BTU surplus of 17,000 times my 10-minute minimum desired runtime, and that's going to give me a cycle factor of 170,000 BTUs. So I have 170,000 BTU cycle factor. Okay. To find out my tank capacity, I'm going to divide 170,000 by my delivery delta T times 500. In this example, my delivery delta T is going to be 20. 20 times 500 is 10,000. 170,000 divided by 10,000, that gives me a 17-gallon tank. So I need to find a 17-gallon tank. But John, the likelihood of me finding a 17-gallon tank is slim. I would go one more than that. It's probably none. What's the closest tank size that you can find? That's what you would want to use. Well, I could get a 12-gallon or a 22-gallon. Okay. If you used a 12-gallon tank, that would be less. So your minimum run time would be less than 10 minutes. Okay, that's all you're doing. You're buying a cheaper tank with a few minutes, or a smaller tank with a few minutes of run time. The 22-gallon tank is more, your minimum cycle time might be a little bit longer than 10 minutes, which isn't a bad thing. So that's the balance that you have to find. Smaller tank, your runtime is going to be less, perhaps more short cycling. Bigger tank, runtime's going to be more. Really no downside to that. If I was doing a radiant system, a residential radiant floor heating system with a delta T of 10 in this example, 10 times 500 is 5,000. Now, if I divided 170,000 by 5,000, I would actually find that I needed a 34-gallon tank. So the smaller the delta T, the bigger the tank as well.